Hello, this is the video for the Lab 3 Part 3. Um, I will be covering the basic setup for the sim. We'll start off at the mesh, on the mesh window. So here's the basic mesh. The plate is defined and the blockage ratio has been calculated so that it is under 10%. The mesh uses triangulation, or triangles method, and has a relatively small element size to allow for better results. And there are four main selections: the walls, the plate, pressure outlet, and the velocity inlet. The Fluent setup is relatively simple. Only a few values have been changed. The inlet velocity changes from between 2 to 5.12. 2 is for the 30 Hz setup. I'll run that right now. The model being used is the standard K epsilon model, and the thermal effects and pressure gradient effects are enabled, as well as the energy method or energy equation. The reference values are changed by clicking on the selections manually, and the initialization is done after the velocity inlet speed is modified. After the sim is initialized, sim is run, and right now it's set to 150 iterations. We really only need enough iterations for it to converge, and it converges after around 75, but just only a couple extra seconds, so I just have it a bit over for safety. So you see here it's converging. It's flattened out, starts to oscillate, it's fully converged, and there you go. It just got all the contours. We'll look at them right now. Here's the static pressure. You can see this aligns with our expectation. Very low pressure region here, and it gradually will begin to gain more pressure, which is the reason why there is an adverse pressure gradient acting on the air particles, which causes backward circulation from the leading edge to the trailing edge. If we take a look at the velocity vectors, you will see it more clearly. You can see that there has been flow separation right here, and so the oncoming air kind of just goes over the flow separation, the boundary layer, and the boundary layer has a very, very visible backward circulation, whereas the air begins to enter an area of higher and higher pressure, it will begin to turn backwards and will travel from the trailing edge towards the leading edge. This is even more visible with the path lines, where you can see the flow separation bubble in much better detail. You can clearly see the path lines traveling around in multiple smaller circles, and stagnation point effects. Now we will quickly take a look at the 60 Hertz setup here to spot any large differences. Initialized and calculating. Just like before, it'll decrease, start converging, oscillate, and roughly around here it'll be finished, and we can take a look at the differences. In terms of pressure, there aren't too many differences. The low pressure region kind of moved slightly forward, but other than that, really just grew in size. With the velocity magnitude, the circulation just became more prominent. You can see between the previous one and the 60 hertz one, between 30 and 60 hertz, it just creeps forward sooner, and it creeps forward with a larger velocity vector. The path lines are significantly different. The internal circulation has grown. It has become more defined, and it has grown, although it has shifted back from the leading edge. It has shifted back slightly, but it has shifted back and grown in intensity. The last thing to cover is how we acquired the forces. Relatively simple. We go to reports, forces, and we can choose the direction vector to isolate specific forces we're trying to look at. Make sure the plate selection is selected. We print it, and we can see that for drag, we have negative 3.8 newtons for drag, and for lift, just change direction vector. We have 21.58 newtons in terms of lift. This is for the 60 hertz. We would repeat the same thing for the 30 hertz. We ignore the pressure coefficients. The coefficients are not very well calculated, so we will ignore that, and we're just getting raw force magnitude. But yep, that is the process for the Lab 3 Part 3.